we have the panel is right after, and then we're gonna end our seminar. Since some people have to catch the 6 o'clock flight, I'm going to make a bus available leaving from here, from the auditorium, directly to the airport at 3:45. So for those of you who are not going to be part of the RTDS presentation, can go directly to the airport because some people have a tight schedule to catch their flights. There will be a second bus at 4:30. So at 3:45 there's a bus leaving from here to the airport. And then when we're going to go to the lab just to see the RTDS and talk a little bit more. And from there, at 4:30, there's a second bus going to the airport. So you have two options for transportation to the airport. From here to the airport, usually it takes 30 minutes. If there's traffic, we cannot preview the amount of time, but I'm sure 4:30 there will be no traffic. So we are going to begin. We are going to begin the afternoon session. Something else I was asked was about the presentations. I have all the presentations from yesterday and today. And I'm going to put this in a flash drive, and I'm going to include a link so everybody can have access to them. All the presentations will be available for you. And the material from Professor Samorodov, there is a presentation and also the text that he read.
Let's start with the work of the performance of synchronous generator during HWL test. Presentation will be by Dr. Luiz from Unicamp. Well, once again, I'm here replacing another professor, Professor Walmir de Freitas, was the one who actually did this work. In this case, I didn't have any participation in this work, but I read a report of 100 pages to bring you some details. The objective here is to try to do some energization studies of the north-south link using the modeling of the generator. The idea is to see the impacts on the generator. You saw several works where the generator was not represented. It's an ideal source of voltage, has some reactance. Here we consider the detailed model for the generator of Belo Monte plant. The idea is to see the transients during the energization and also to study the occurrence of defects during the energization study to see the intensity of the transients that the generator would undergo in case there are faults during
этих напряжений, которые это
the preparatory studies for the test. Sorry. Half wavelength link. I don't have to talk about it. Professor Walmir studied two scenarios. The first one in which the report study energization, and during the test, 3-phase and single-phase short circuit, and then there was a report. But only one machine, etc. So we've redone this report on those two studies. What is the study that uses only one machine? More important about the generator. When the impacts were divided among the three generators, we didn't see great problems. In case of one single generator, especially the fault situation, there may be some more serious transients on the generators. We use the PSCAD for this work. The line model is the same model that everybody from Maria Cristina here is using in all studies. What we've done is that we included the model of the generator. From where did we get the data to represent the Saturday Mesa generator? Here in the reference case of electromechanic ANA 10 format. You can find this at the ANS website. You have all the data for the generator, for the voltage regulator, turbine data, speed regulator. You find all that there. The models available in PS cards in ANA 10 are different. We worked the conversion of the data so that we could use those data in the standard of the models that were available in the PS CAD. So here is give you an idea of what was modeled. Here is the model of generator in PS CAD with all data converted from ANA 10. What we modeled was we didn't model the turbine and the generator. What we want to see is the transients on the generator. So what we want is the most detailed as possible electromagnetic model for the generator. The electromagnetic transients is not important because the duration of the transients is not long. You don't have enough time to have any response in the mechanic terms. So this model of generator considers the possibility of the ATP, that is PSCAD, but you can consider that the speed of the generator is constant. So you're not going to see electromagnetic transients, only electromagnetic transients, because it's what really matters to us. In the grounding part of the structure part of the generator and settlement, we couldn't identify. It was not available. So we tested two extreme situations. Isolated stator and solidly grounded. We simulated both cases. Then we have the detailed report for those of you who want to analyze those results better. But we've done a series of studies. The generator with automatic control of tension, voltage. We modeled the AVR. The VR in the case of an antenna is defined by the user. In PSCAD is the standard 3A model. So what we did was try to adapt the data to try to get as close the VAR of Saturday with the models available at PSCAD. What we did, we carried out energization tests, and after energization during the test, the fault, three-phase and single-phase faults, short circuits. I'm going to show that at 3/4 of the line, which are the worst cases as it's known. Then we did the test with the constant excitation. So during the whole event, VAR does not update the field current in the machine. I'm not going to show you this here, but this is in the report. What we did was also the test with the reduced voltage at the excitation to reduce transients. Instead of doing the voltage of 1 pu at the end of the terminals of the generator, what we did was working with 0.09 pu, reduced voltage once again with the VAR activating during test or with the VAR blocked. So there's a series of tests which I'm going to show results only of this first part here. The conclusions in general are the same in all those study groups here. So how was this test performed? First we started the generator operating with no load situation, adjusting the voltage in 1 pu. The voltage at the end was 1 pu. We closed the circuit breakers. Normally after 1 second this transient of the startup of the generator has reached industrial frequency. We do the simulation. After 1 second everything is established and is stabilized, and then you're going to close the circuit breakers of the 3 phases at the same moment without any method to try to minimize or diminish the transients. No detection of zero for the switching, nothing. Just switching at any moment randomly. So the closing moment was 1.86 seconds here, because after 1 second everything was established. The machine has 1 pu and it is generating, working in industrial frequency, ready to energize the line. After 3.5 seconds, the circuit breakers open again. So it's gonna work 2.5 seconds. Then the closing of the line. maximum overcurrent values in the half-wave line is 188 pu, according to the middle of the line. Here are the ends. Minimum values about 0.06 pu in the middle, 0.88 pu at the middle of the line. It's interesting to show with those tests that were done with the generator. The main objective is to see the transients on the generator after the energization. This chart here shows maximum the voltage during the transient during the whole test in each point of the line. Here at the end of travel, here at the entrance of the line, 10-20% exit of the line. So we have the biggest over voltages at the entrance of the line, the smallest ones at the end of the line. Those values are not different from those values that were obtained when you simplify the modeling of the generator. Those would be the transients in the beginning and the end of the line. So if it's a transient, you go from 188 pu, and then in the industrial frequency you get to 0.0 pu. That energization without any faults. What happens in generator? Active power is demonstrated here. You have a transient of active power, then after less than half a second, generator goes to industrial frequency, 0.04 active power, the base of the machine, 470 MVA at the base of the machine. So those are the losses of the line during the test, is around 200 megawatts. This is what is supplied by one generator. When we do the test with 3 generators, this is divided amongst the 3 generators. Reactive power, one transient after the energization, and then the line put reactive in the line, you absorb 0.5 pu of reactive power. So during this generator is going to provide 0.04 pu of active power and absorb 0.05 pu of reactive power in industrial frequency. That shows the VR working. First to adjust the voltage in pu after the startup of the machine, then switch in between the limits at the initial transients after energization, and then it recollect the field voltage in industrial frequency because it is already sending some inductance into the machine. So the load increased, so it was working with no load. Now it's meeting the losses and it's getting a load angle of 10 degrees. So current of voltage in the machine. Here is the current of one transient of 2 pu of current, but short duration. Something like 100 to 100 milliseconds. Here the current drops, gets to 0.6 pu during the test till the closing of the line. So we have a transient of current here that is short-lived. The amplitude is 2 pu. If you have, when you do the energization, excessive reactive onto the machine, so the voltage goes up, but the VER can regulate it, bring the tension back to the reference of 1 pu. When you have the disconnection, now you don't have a field in the machine, the voltage falls and the VR works once again to bring the voltage to 1 pu. Here is no load, here is energizing the network. Here are the voltage values in RMS. Here, during the energization, would be the energy dissipated in the surge arrestors during the no fault energization test. So practically all surge arrestors dissipated a quantity of energy, but all here in the order of kilojoules. A quantity that is a small quantity of energy in the dissipation small. There is a gap in imperatives. In this case of energization, the gap has never actuated, never got to actuate. Here would be the chart that shows the operation of the imperatrice gap. The idea of this gap is in case of short circuit to diminish the length of the line. So you cut the line from imperatrice on, the machine is only energizing the line only up to imperatrice. Faults. During the you do energization, after a while you see that stabilizes. you make a fault to see what happens to the generator in case, for instance, there were faults during the energization test of the line with half wavelength, single phase and three phase. That was the scanning of the whole extension of the line, but I'm going to show you here only around 3/4 of the line. The fault is always applied in 2 seconds and it's eliminated in 2.5 seconds. So we will keep the second for 400 milliseconds, precisely to analyze what the impact has on the generator. Fault resistance used was 10 ohms. I do not know where some values came from. Perhaps Cristina does. Very well. Let's go on and see the results. I've spoken about all this. The voltage of the generator, 1 pu. In this case here. And then we also had the study with the reduced voltage. Now we have short circuit, 3-phase fault in 3/4 of the line. Here are the over voltages that appear in each point of the line. We had the over tension or over voltage of 12 pu in the beginning, and then in the middle line we had the valley of voltage. But during defect, you're going to have over tension, over voltage here in the middle line. Here's the maximum value of the over voltage during short circuit, below 2 pu. And the behavior in this case of the line was different. That was the actuation of the Imperatriz gap. So this shows the voltage in Imperatriz. So it falls to 0 upstream of the gap because the whole part of the line was turned off. That would be the transient of voltage in Imperatriz here in Guru P. From Imperatriz onwards was turned off, and from Imperatriz to Serra da Mesa the line is still energized but with under voltage, 0.4, 0.3 pu of voltage. Even after the elimination of the filter gap continued downloading energy in Imperatriz. Active power in the generator. Let's look at the generator now. This is energization, what we've seen. We provide certain active power here, 2.5. It was in 2 seconds we had a short circuit. So if you have a transient of active power in 2.5, here in 2.5 the short circuit was eliminated. The generator continues energizing. That is, in 2.5 there is no longer a short circuit, and then the gap actuated in Imperatriz, so it was even shorter. So the quantity of active power that the machine is still providing for the line only of Serra da Mesa to Imperatriz diminished. But the reactive power grew a lot. So the machine was here, wait, it grew a little. It's around 0.6 pu of reactive power after elimination of the fault. The fault lasted 500 milliseconds. And here all actuation of the VAR, here it can regulate the voltage. Here was still regulating. There was a short circuit. During the short circuit, the VAR cannot regulate the voltage. After the short circuit is eliminated, it increases the field current to almost 2. Maximum value is 5 at the transient system. And after the elimination of the fault, it adjusts the voltage of the generator and bringing it close to 1 pu. Here's the load angle because it fell because part of the line was diminished because part of the line was disconnected. So the line was shortened. Here's the voltage profile on the generator. We had a voltage. Here's current. Here's voltage. We had around 2 pu voltage during energization, but with the 3-phase fault, this transient grew a lot, grew some. There is a greater current transient, but it falls quickly too in the short circuit for 500 milliseconds. And here, the voltage. What happens with the voltage during short circuit? There is a dumping, there is a decrease in the 3-phase. The current transient grew a little, and also the resistors dissipated the energy, and there is also the gap. Here's the energy dissipated in the surge arresters. In some surge arresters, energy grew a lot. You cannot read those numbers, but in some of the cases it gets to some megajoules, whereas in energization it was only in the range of kilojoules. Then you can see those figures properly. Here is the current at the gap. So, at the moment of the short circuit, only in 2 seconds, and then starts dissipating. The short circuit was eliminated in 2.5 seconds, but it continues dissipating energy. It only stopped dissipating energy when the line was disconnected at 3.5. Here is something that appeared in the simulation, perhaps excess current sustained in the gap, showing that the protection would have to actuate quickly to turn off the line in case of three-phase short circuit. The short circuit couldn't last 3 seconds. Monophase short circuit, there are over voltage in 3/4 of the line. At the 3/4 of the line, they were smaller compared to the over voltage in case of three-phase short circuit. Here, what is this here? As the short circuit is now unbalanced, you have the three-phase here. You cannot see the three phases separately, but some will go up, some will go down. But this shows the short circuit in each point. This is in Bom Jesus da Lapa at the end of the circuit. Bom Jesus da Lapa. Something different that occurred here in the single-phase short circuit upon the generator. It continued providing high quantity of reactive power around 2 pu during the whole existence of the short circuit. So it provided 2 pu of reactive power and more than 1 pu of active power sustainably until the short circuit was eliminated. That had not happened before in the three-phase short circuit. This thing here shows the behavior of the AVR, the VER, and here is the load angle. The load angle was here oscillating too during the whole existence of the short circuit. This here shows the currents. So, in the short phase, the blue phase here, you're going to have overcurrent, current around 2 pu, and differently from the three-phase case, it is sustained. The silver current is sustained, which means the protection has to operate quickly in the case of fault. 5 minutes. The voltage profile is not equal to the 12 phase during short circuits, and here let's just ask, in case we have isolated neutral, you're going to have neutral voltage that will appear for the imbalanced short circuit, but it was low, perhaps not enough to, in case here with the grounded neutral, solidly neutral, did not exist. It was the neutral current that appeared. Here the isolated neutral, here is the grounded neutral, but appeared, but not enough perhaps to detect a single phase fault, low neutral current. Dissipated energy in the surge arresters. In the case of the single phase short circuit in 3/4 of the line, there was no triggering of the imperative cap. Only the surge arresters were the ones who dissipate energy. So the conclusions of this report, based on the obtained results, we can see that the transients caused by the energization of the line of a little more than half wavelength are not severe and do not mean risk for generators. We have to remark that the simulators were not carried out using controlled energization of pre-insertion resistors, which would result in diminution of transients. In case of short circuit, it was verified that depending on the defect of the transients, that does not generate greater severity on the generators. However, especially for short circuits close to 3/4 of the line, the occurrence of three-phase or single-phase short circuit can cause severe transients to generators, so that the protection has to actuate quickly to protect the line and equipment. So, The main conclusions of this work are those.
João Lima from Potência. Professor, the purpose of your simulations, from what I have understood, is to verify the maximum demands on the generator or generators in Serra da Mesa, this both over voltage and over current demands. The representation used for the machine, I understood, was the Model 4, everything complete, and you had the opportunity to include the voltage regulator. So my first question, it's more curiosity, is up until the 30 cycle or 500 milliseconds, what was the influence, if you detect any, of the presence of the voltage regulator? And the other question would be, if I have understood correctly, the closing instance for the maneuver and the closing instance for short circuit were determinant. It's what I believe, I'm not sure, but the question would be, why didn't you use, at least for the most severe cases, the energization process with common usual statistics? And in the case for short circuit, why not use the systematic process, which is also usual? Could you comment on that, please? So regarding AVR, right? So all the studies showcased was conducted when AVR does not respond, it's blocked. The results were very similar with AVR working throughout this phenomena. The difference between overvoltages and overcurrents was not significant. Something else that was tested was the network energization with low voltage, 0.9 pu instead of 1 pu. In terms of overvoltages and overcurrents in the generator, the results were not so different. This is all part of the report. But from what I have read in the report, these times were always determinant. I'm sure it could have been done in a better way, but in my opinion it was done this way because they were concerned about the effects on the generator. The focus was the generator. Is that, Cristina? Is that it? It is because in reality the points were chosen. This time is determinant, but they're trying to get the worst condition. Since when the fault happens in this 3/4 region, we are basically getting resonance. It's not exactly the transient that is going to be the most important thing. So if you adjust the instance a little bit more, you can get a small difference, but what's really strong is the local, especially for three-phase. With three-phase, the problem is a strong resonance that comes up and it's sustained. So the transient part, there will be some different in it, but we're talking about 1/10 of a pu. And what's important here, in local, you're going to have about some pus. So it's very different. Systematic could have been done, but we wouldn't get values that would be much different. What's important for the three-phase is that when you apply the defector at 3/4, the tap acts immediately. So if you change a little bit the instant, the gap is going to continue to work instantly, removing the resonance. For the single-phase one, perhaps if you do a systematic scanning the whole cycle or half a cycle, you could have gotten some differences. But we're only working with 0/10 here. But anyhow, when you close with the three phases exactly at the same instant, you have no guarantees that this result is more critical than closing with 200 statistics simulations, for example. And perhaps if you're analyzing the supportability of the generator to the demands or the requests, you would have to ensure that it is being requested in the simulation by the maximum level, and perhaps this value cannot be the maximum value. So our suggestion would be, for the most critical cases, do at least one statistical simulation. This could be done, there's a fact, but it's not going to be very different in terms of severity for the generator, but it can be done. From the moment we identify the worst region in terms of location for defects, we can do this. But I'm not sure if Professor Walmir did this, because he's not presenting here, and this is an older report. I'm not sure if he did or did not do a statistic, but if it can be done in either way. And just to finalize, I believe that your voltage regulator on the 30 cycle period, or 500 milliseconds, it was not effective, or the results did not present to be different because your energization did not impact the terminal voltage. The terminal voltage was not so different. It did not demand from the regulator an effective action. Is that true? There was a voltage transient on the generator, but it's very fast. What we saw in a situation like this, it goes to the limits. AVR goes to the limits. It's only going to act when the transients are more damped, and then we can adjust it. I imagine, I couldn't talk to Professor Walmir either. He traveled and only left me with the report, but I'm sure he conducted several tests. But I only have access to the ones that are part of the report. From what I have understood, it was always, the instances were always determinant. Question? The system is very complex. There are several variables, but I'm a little intrigued about the gap. So I have some questions about it, because if I understood it correctly, this is an interesting moment for us to brainstorm a little bit and have some possible ideas. You showed on your last slides related to the three-phase fault where the gap works. If I could see it correctly, the Christ currents for that fault condition that you were causing, and after that a stabilization about 2 kiloamperes for the crest, and you show that after the elimination of the fault, this one exactly, after the elimination of the fault that was generated for 500 milliseconds, the current would be maintained in case the system was not turned off in this 2 kiloamperes of peak. You did not present it here, but my question is, do you have the voltages that were present throughout this period of time? Can you get this? The voltage in Imperatriz? No, the voltages on this gap. Yes, this would be the voltages in the Imperatriz substation. I imagine, yes, this was the point where you included the gap. Just for me to get an idea for the debate later, I would say that the voltage in the substation of Imperatriz, it's around half PU, 200 kV, and then it starts to escalate. You can notice that here the time axis is too open, but it starts to go up very quickly in the second graph, right? No, the first one, where the pointer is. This is the Imperatriz. The first one, you show that the gap eliminated the voltage, right? In an effective way. In 1.6, the gap starts working. This is the voltage in Imperatriz. It was at 0.5 pu, and then the FET happens at 2 seconds, and then voltage starts to go up. When it reaches 2 pu, the arc is broke. sorry, when it reaches 1.6, the arc is broken, and then you have that arc current there. It did not exist, and at 2 seconds, the arc is broken, and as soon as the short circuit happens, the voltage goes up, and the arc is broken. When it reaches 1.6 pu, the arc is broken, and then it removes the line from the quasi-resonance or resonance condition, because now you start having a short circuit in Imperatriz. You don't have a short circuit at 3/4. It's a 3-phase short circuit. We monitor the 3 phases, all of them work, and then you start to discharge. You can remove the short circuit, but you're still feeding until you turn off the line. It's going to continue, so you have to open the circuit breaker. It was capped until 3.5. So until you open the circuit breaker, the short circuit is going to be there. So you do not have the short circuit at 3/4, but you have the gap. The gap is not controllable. It's going to maintain the arc until you open the circuit breaker, until you remove the voltage. So just another question to make it clear. From yesterday until today, all the simulations that were shown for single phases, this gap did not happen. No. No, at any moment the voltage in Imperatriz reaches this value. If it reaches this value in the substation of Imperatriz, for example, the gap, since we're talking about an insulation chain, you could work on a more rainier day, and the gap work in a lower tension, voltage 1.4, because for the energization to be done, it's very low, 1.2. But for the energization with a single fault, I think it's 1.45 or 1.5 for the single phase fault. So it's not a critical point. So if the gap works for single phase fault, this is not a problem. It's not a problem. No, for a single phase fault here, it's not a problem. And do intend, in case of a single phase fault that causes a change in the gap, do you expect to treat it as a single phase fault? Meaning trying to recompose just the phase that is at fault and maintain the other 2 ones energized. This is done for the study. This methodology was developed for the study, so we can protect it and conduct the study. The idea is that during the studies to do an energization without faults. We're not going to go forward as the Russians did, because in fact, indeed it can happen. For example, like Valdomiro's airplane, it could crash there. Yes, if a single phase fault happens, or a 3-phase fault that causes the work of the gap, or a single phase fault that makes the gap works at a lower voltage, the fault at Imperatriz, or a single phase fault in Imperatriz, is not going to be severe. The protection is going to work. But since what is expected is for the gap only to work for the 3-phase. We have varied it until today with statistics, and it still hasn't happened. Thank you very much. We'd like to thank Luiz Carlos for his presentation.